Alright, welcome to the next lecture of this week. So we're going to finish up these slides, and we stopped on a very suspenseful moment. I was going to show you how to use Makefiles to automatically compile/recompile the program that we were talking about last time, this library involving all this searching, binary search, linear search. Okay, so this entire library, we can make a Makefile. We can make a Makefile to go and compile these things. Okay, so here is the idea. We're going to make a Makefile for our searching library. We have searching.cpp and main.cpp to create object files out of, which means we need a recipe for, we need rules to make main.o and searching.o. Okay, that's the idea. And then we need one more rule to make main the main file that is executable. Okay, that'll link together main.o and searching.o. Okay, so that's where we're going. Let's make it happen. Let's go back to this to remember how to make these rules. Okay, so what we'd like to do is make rules that create main.o and searching.o. So those will be the names. That's the thing that we want. Okay, here we go. So let's make a new file, and it's got to be called Makefile. Okay, that is the name of the file. It's silly, but it is. That's what it has to be called. Okay, and so their first rule, let's make it be for main.o. Why not? So what we want, that's what we want. And so these are comments, by the way. Comments in Makefiles start with number signs. So if you're familiar with Python, that shouldn't be too different. So that's what a comment is in a Makefile. And so what we want is main.o. And what we need in order to make it is main.cpp. Can't make main.o without the actual cpp file. So that's what we want. That's how we, main.o is what we want. Main.cpp is what we need to make it. And then we go and we tab in. My editor did it automatically for me. And then we say what needs to be done. We put terminal commands in here that get us to what we want, to the name of our target, which is main.o. And so how do we make main.o from main.cpp? We say g++, with our fancy stuff, and then we say main.cpp, but before all that we say -c. Okay, and this will make main.o. See that? And we can do the same thing for searching.o. It needs searching.cpp and searching.cpp. See that? That's quite nice. And then one last one for main. That's the final thing that we want. What do we need in order to make main? We need main.o and searching.o. So the Makefile will actually take care of making these things if they don't exist. And then to finally compile them, or to link them, sorry, after we've got the .o files, we just say main.o, searching.o, because we know we have them now, -o main. And that gives us, finally, the thing that we wanted, which is called main. Okay, usually is the thing that you want is the file name. Okay, so these are our rules. One to make main.o, one to make searching.o, and one to make main. This is the entire Makefile. How do we use it, you might ask? So make is like a little program, and you can run it. So if you want to run a Makefile, you say either make target name, which makes the thing that's to the left here, to the left of every colon, you can say make main, make searching.o, make main.o, or if you want, you can use make by itself and it will run the first rule. Okay? So normally people put the most important thing there first so people can run make. So if I wanted to, I can move main up to the tippy top, but that's okay. So if I just say make, it will run make main.o. Okay? I just say main, make like that. So here we go. That's what it did. It just made main.o. And so it needed to run this command, and it did, and it made it. I could have alternatively just said make main.o with the actual name of the thing, but because it was the first thing, it got run automatically when I just said make. And notice, if I try to do it again, it noticed that it doesn't need to remake it. It's like, oh, it's up to date, dude. You don't have to try anymore. Now, that's the key. So if it doesn't need to change, it doesn't change. And then main, if I say make main, here's what happens. It notices it has main.o already. We've made that. It doesn't know where searching.o is, but it knows there's a rule for it, and it knows we have searching.cpp. So it will run the rule when we just say make main. It will make first searching.o. It needs it. It knows it needs it. And then it will finally run the rules, once it has both of these, to make main itself. Isn't that cool? That is Makefiles. And if I say make main again, it's like, no, it's up to date. You're good. I hope you can see how useful this is and how useful it's going to be. So one thing let me do is, let's remove everything. Remove main.o, and searching.o. So we're back to a clean slate. And if I say make main, it notices it needs everything. So it makes main.o, runs that rule. It makes searching.o, runs that rule. And then it finally runs the original rule that we wanted once it had those things. Isn't that nice? And then one last thing is, remember, or did I say it? If anything changes, it'll only rerun the relevant rules. So if I change main to, say, exclamation point, hi mom, make main is going to do this. It's going to look at the Makefile. Oops, sorry. There's the Makefile. Let's get rid of that. There we go. Make main is going to look at the Makefile, notice that searching.cpp hasn't changed, but it's going to look at this rule and say, okay, main.o needs main.cpp, but main.cpp has changed. So it will rerun the make main.o, and then also rerun main. It'll skip this rule though. Okay, hope that made sense. So it only reruns the rules that need to be rerun. Okay, that is a tongue twister for me. So notice that it skipped out on remaking searching because that didn't need to be remade. That's the idea. And so now we've got hi mom with an exclamation point. Okay, so hopefully you can see how useful Makefiles are. And yeah, that's essentially where I want to leave you right now with that. Or maybe just to make it extra fun, maybe I should introduce some of the shorthands. I'm considering that. No, I'll do it in the lab if I have to. Never mind. Let's leave us there. Let's ruminate on that for a while. Okay. The next thing that I do want to talk about, though, is complexity. So how do we determine how fancy an algorithm is? Okay, so let's learn a bit about complexity. This is really a topic for CSCI 41. So if I test you on any of this, here's my disclaimer. If I test you on any of this, it will only be through multiple choice questions that are easier than usual. Okay, so that is my promise to you. So complexity. How do we do it? How do we discover the complexity of an algorithm? And the goal is, the way to do it, the way that people decided to do it, is to count what I will call the number of basic operations that an algorithm takes, okay? And then we can compare that number across algorithms. So we can count the basic operations for linear search, and then we can count the basic operations for binary search, and see which one was better. That's the idea. Okay, so that's how we compare complexity in computer science. And so what is a basic operation, you might ask? It is one of the following things. It's something like an assignment and a bit of arithmetic, checking a condition, so like an if statement. Usually, it's just one line of code that doesn't do anything fancy like make a loop happen or call a function that loops. Everything else is one basic operation. So like int x equals 5 plus 2, that is an addition plus an assignment, so that's like 2 basic operations, okay? Don't worry, you'll never have to count this, but this is the idea, okay? So, yeah. If you do this kind of counting, though, and you're extra explicit like I am, you don't ever have to be this explicit though, it will tell you how fast it is mathematically, which is quite nice because our computers in our phones are a bit slower than our computers at home. So this gives us a way of comparing the same algorithm, even if it's going to run on different processors with different speeds, because it'll still be the same number of basic operations at the end of the day. Okay, so yeah, this is not enough just to count the number, because a lot of times our functions, our operations, our algorithms are variable in something. Like linear search, for example, takes a vector and then like something to search for, and this vector could be huge or it could be small, and that really depends, or that really controls how fast linear search is, right? It's very quick to go through a size 3 vector, and it's very slow to go through a size 1000 vector linearly. So we have to somehow include like how big something is, and our number of basic operations can depend on a variable. Okay, usually we say it's called n a lot of the time, so that can be like the size of our vector v, and that will give us a better number to use to compare against like binary search, for example. Okay, so that is the idea. Again, I'm not going to test you too hard on this. Your book goes into a little bit more detail than I'm going to go into here, but I think this is all going to work out. Okay, so let's count the number of basic operations for linear search. Okay, so I'm going to be a bit pedantic, but you never have to be this pedantic. You'll learn in CSCI 41 why. So here is the idea. How many basic operations does linear search take? Depending on the size of v. Let's say that the size of v is n, okay? So what do? Well, we have to loop. So this is the initialization takes one basic operation, right? So we have loop init. That's one basic operation, and then we repeatedly do the body of the loop. So this line and then all these lines, they get executed how many times? Well, it's based on the size of the vector v, right? So, and we're calling that n, v.size. Let's call that n. So then we say do n times the following. We have the comparison, which is a function call that takes one basic operation. The comparison takes another basic operation. This method call takes another basic operation. The comparison takes another basic operation. So that's 4 so far. We're potentially returning. We'll just count it even though it only happens once, and then we'll stop. So this is like the worst case. So if we had to keep on comparing, keep on searching, this is 1, 2, 3, 4 basic operations, 5, and then of course at the end of every loop we have I++. So that's going to happen again one more time. That's one basic operation, essentially. So 1, 2, 3, 4, 5, 6. So 6 basic operations. And then I think that's it. So that's the worst case. And then finally, we do I++ one last time, and then we compare once more and notice that we went too far. Like I is now bigger than it should be. Okay, so it's equal to the size now, which means we can stop. Okay, so there's like an extra 1 op to do that last comparison that stops the loop, and then finally, in the very worst case, we're down here and we're returning, which is another basic operation. That's 1. Okay, so 1 more. So really, you can say 1 op, 1 op. And so what's the mathematical formula for how many basic operations this took? It's essentially, okay, 1, 2, 3 plus 6n, okay? That's the idea. That is, depending on n, how many basic operations we have to do in the worst case, okay? That is the idea. Okay, let's do the same thing now for binary search, okay? But we have to get a bit fancy to know, when do we stop? How many times can we have the search space? How many times does while loop execute its body at most? And the answer happens to involve logarithms. So how many times can you have something, which means divide by 2, and still have something left? Like integer divide, 42 divided by 2, divided by 2, divided by 2. How many times can you do that and still have something left? It's log over 2 times. Or sorry, log base 2 of n times. That's the idea. Log base 2 of 42 times. So, again, we have a bunch of basic operations up here, like 1, 2, 3, let's say. 3, and then, in the worst case, we do the following, log base 2 of n times, because that's how big the vector is. Okay? So these numbers don't really mean too much. Like these constants, they're really not going to mean too much. I'll show you on the next slide. But it's important to come up with these n's and these log base 2 of n's. Those are the important bits. So, okay, how many basic operations for a single loop execution? Let's figure this out. Okay, so like 1, 2, assignment 3, 4, assignment 5, comparison 6, 7, assignment 8, comparison 9, worst case, remember, 10, 11, 12. Okay? In the worst case, we do all of these. Doesn't really ever happen, but let's just pretend that we did. So that is the idea. If the whole world went wrong, that was like 12, right? We got 12 hops. And I think we also had return -1 somewhere down here, right? So I think I skipped that, but return -1 if we didn't find it, and that will be 1 up if we got there. Okay, so this is essentially like 4 plus 12 times log base 2 of n, and that is like the mathematical formula for how many basic operations binary search takes compared with linear search. Okay, so what I'd like to show you now is that these, there is a winner. Binary search is a whole lot faster than linear search, and let me show that to you, okay? Looks like last time I counted it a bit differently. This was like 12 and 4, and this one was 6 and 3. Doesn't really matter. But it may look like this is definitely smaller, right? Like this is the better one. Linear search is the better algorithm. It's the faster algorithm, which is not true. Because for large n, watch what happens. Let me give you a dramatized example. So here is my graph of, maybe in blue I'll graph this function, and in green I'll graph this one. Here's what happens. 6n plus 3, that is linear. So it's going to be a line, like here's 3 and here's 6. Then this one, it may start out taking more stuff. For small arrays, it may like fiddle around down there. But eventually, what does a logarithm graph look like? It looks something like that, right? Something like that, I think. Yeah, that's better. And eventually, it's going to come out on top, because look at how the green graph is going, and look at how the blue graph is going. It will eventually win out in the long run for large n. Okay, and you can put these both in your calculator and zoom out and see when it stops being good, but this is the idea. This wins. This is smaller, faster in the end. So binary search, if you can use it, if you have a vector that is sorted, it behooves you to use it. Okay? It's going to win out, especially for very large n values, for very large vectors. That is complexity. Okay? So that is the idea. And then there's a way in computer science, and you'll definitely learn a ton of this in CSCI 41 if you take it. There's a way to like get rid of these useless constants because they don't really mean anything. Like it tricked us into maybe thinking that this was faster than this one. There's a notation that we use in computer science to get rid of these little constants and things that don't matter. So that we notice like, oh yeah, it's log base 2 of n. That's totally better than n. those were the things that mattered. Okay? And so we use what's called big O notation, and sorry I have so much words here, but it takes a bit to explain. So for big O notation, what we do is we take the highest order term, I should say, and we drop everybody else. So for example, the 6n plus 3, we only took the 6n. That, like, the 3 doesn't really matter as n gets large. That's the idea. Then we also drop the constants, so now we just have n. And we call it big O of n. That was what linear search is. We say linear search is big O of n. That's what we do. Okay, so just let me entertain you with these other constants that I got last time, the way that I counted then. What you do is you take this number, take this function, and drop everything that's not the biggest term, and then you also drop any constants out in front of that biggest term. Okay, so both ways still. Told you it didn't matter. Linear search is big O of n, we say. Okay, and we call that linear time. And this is a kind of shorthand. It gets rid of like useless information. Okay, it tells us, it tells us how fast something grows. And usually we use this for algorithms. Okay, it tells us how fast our algorithms grow. And that is a very good approximation for how fast our processor can execute this program. Okay, so that's called linear time. And then binary search, pretend that this was the actual formula for it. You drop everything that is in the highest order term, so you keep that, and then you drop any constants out in front, so it's log base 2 of n, and so we say that binary search is O of log base 2 of n. And we use logarithmic time as the fancy word for this. Okay, that's big O notation. Your book will talk a bit about it. I'm not really going to test you on it. It's just a nice way of reasoning about algorithms. And yeah, you'll definitely see it more in CSCI 41 if you take that. And that is in stark contrast to doing something like this, where you like actually use real time and you try and figure out like, okay, linear search took 0.573 seconds and binary search took like 0.483 seconds. That's really hard to determine any winners based on that, especially when your program is running on a computer that's running other programs that are taking up time on the processor. So you can use it this way. You can profile your programs, time them with real times. With CTime, you can use these clock t's and then subtract those and divide by clocks per second. That's the way that you can do that. But what you get back is not really anything useful. It just has to do with like how fast your computer was running at the time and like the inputs that you gave to these algorithms. Whereas these numbers, these never change. O of n versus O of log base 2 of n, that tells you immediately, yeah, we're going to go with binary search for sure, if we can. That's the idea. Okay, so that is complexity, how you can determine how fancy an algorithm is. It's a very fun concept. Please yell at me about it if you don't have any, or if something is going wrong, if it doesn't make enough sense. This is something that will be ingrained in your mind, though, if you take CSCI 41, so don't worry too much. And now, I think, yeah, the last section of these slides is about sorting, which is another thing that I'm not going to test you very heavily on. It's another CSCI 41 topic, but it's something that I want to like work into your mind now, of course. So just to get you ready. So again, if I test you on any of this, it's going to only be on multiple choice questions that aren't too hard. That is my promise to you. Okay? So let me show you a bunch of different algorithms, and I'm going to give them to you in this kind of pseudocode style, where it's not like there's no return value. What is going on here? You can just kind of read this as it is. Okay? Numbers is supposed to be an array or a vector, and number size is supposed to be an int, you can assume. So I'm going to show you different kinds of sorting algorithms, and I'm going to tell you how fast they are asymptotically in this big O notation so that we can see which ones are the winners. Okay? So there's a nice little website that I've opened which tells us, like it gives us a nice show as to how fast all these things are. And I wonder if I can zoom in any more. That's about as good as it gets, I guess. So it's going to show us what bubble sort is doing. This is the code for bubble sort. You can see it's got a bunch of for loops and then an if statement. Here's the idea. Here's what bubble sort does. Okay, so dun dun dun. Here's what we do. Bubble sort takes an unsorted array. These are all sorting algorithms, so they take an unsorted array and they update it in place, usually, to be sorted. So you got your 3 and your 5 and your 6 and your 7, oops, and your 8. And so that's what sorting does. Bubble sort will do it. All these other algorithms will do the same thing at the end of the day. But the question is, how fast do they do them and how do they manage this? What bubble sort does is it swaps elements that are next to each other that don't look right. So it'll take the 8 and the 6 and it'll swap them. Like, okay, I should put a, let me rewrite that, I think. Bubble sort, what it does is, down here, it notices that 8 and 6 are out of order. And so what it does is it will swap them, 6 and 8. And then it moves its little arrows. Then it looks at, oops, I guess I have to erase. And then what it does is it looks at the next two. It's like, okay, what about 8 and 7? Oh, those are also out of order. Let me swap them. And then it'll do the same thing. See where I'm going with this? And then it'll swap 8 and 5. Because those are also out of order, right? So now we have 5 here and 8 here. And then it'll notice that it needs to swap 8 and 3. Right? And it'll swap 8 and 3. And it'll put the 3 here and the 8 here. So it goes through the entire array once, and the only thing that's in the right spot is the biggest value. Okay? And then it notices that it's done with this, and it goes through the entire array another time to get all these in the right spot, to get the biggest value over here. And it goes through it all again, up till there, to get the biggest value there. And it goes through it all here. It just keeps on swapping elements that are right next to each other. That's what bubble sort does. I won't explain it anymore. That's essentially the idea. Let me show you it graphically, though, because it's fun. So here's it like in red, comparing things, and it's putting the biggest value in the right spot. Every iteration that goes through the array goes and puts the biggest value in the correct spot. Okay? That's what happens. So it has to do this how many times? Well, it has to go through the entire array, essentially, n times, doing n amount of work, right? That is essentially the idea. 2 nested for loops that both go through, on average, the entire array. Okay, I don't think I can make this go any faster, but I think you can imagine what's going to happen now. It's just going to keep on putting the biggest value, the biggest value, the biggest value, keep on swapping things. So now the biggest value is there, there, there. It's quite slow, right? Even with this fast animation, it's as fast as I can make it go. So skip forward. It's going to eventually be sorted, but at what cost, right? So this is a doubly nested for loop, and the I is keeping track of like how many times have we gone through the entire array, and that is, then you also need to go through the entire array again with j, so that you can swap everybody that's right next to each other, j and j plus 1, right? So yeah, you can feel free to read this. I think I've explained all of it, but this is going to take, it's going to go through all n elements, and this on average will go through n elements each time. So this is big O of n squared, and we consider this to be very slow as a sorting algorithm. Bubble sort is kind of the worst algorithm, but it's the easiest to talk about. It makes the most sense as we're starting out. Okay, so that is bubble sort. Let's talk about some fancier algorithms now. This one's called selection sort. So what it does is it goes through the entire array, whatever it may be, and it goes and finds the minimum value, like maybe it's -1 or something, and then it puts that minimum at the beginning, and it knows that now it's done with that value. And then it can find the new minimum in the rest of this, and maybe it's like 2, and it can put that there in this index, and now it's done with that index. That's how it works, okay? It selects the minimum. It tries to fill in that location I each time with the correct value, okay? So again, it has to go through the entire array, and on average, inside the inner loop as well, the entire array to find the minimum of this little sub-array. So it's still O of n squared, but it's slightly faster than bubble sort because there's less swapping. Okay, you go and find the minimum. You don't have to like swap random elements. That is the goal. So again, I'm just going through this very quickly. I don't expect you to memorize any of this. Oops, sorry, it's already sorted. Let me, how do I stop? There we go. Let's randomize the array. There we go. And we want to do selection sort. So it's going to do, it's going to find the minimum. It has its, like it's highlighting in red its current guess of the minimum, and then it's going to put it at the front of the array where it thinks it needs to go, the next possible spot where it could go. Okay? And so I think you can tell how much faster it is to bubble sort. All these comparisons, all these things are taking the same amount of time, and it's already a third of the way done, a third of the way sorted. Okay? So that's quite nice. And that is selection sort. Okay. And so, yeah, it's almost done actually. We can actually watch it to the end. Yeah. So that's selection sort. It selects the minimum and puts it in the next spot that it's considering. Okay. That's selection sort. It's O of n squared. It's quite nice. That brings us to insertion sort. So what this one does, this is like the best n squared algorithm. It's still n squared, of course, but it's the best one, we say. So insertion sort is a bit weird, but it's quite efficient in many cases. So let's see how I want to explain this. What it's going to do is, different to selection sort, it's going to keep a sorted first half, if that makes any sense at all. So I'm going to show this to you like this. Let's pretend that the array looked like this, maybe 8, 6, 7, 5, 3 again. That's fine. What it does is it keeps a sorted version of the first 3 elements. It doesn't put 5 and 3 over here yet. So when I gets to be here, this part of the array has been sorted with the original values that were there. So it will turn this into eventually 6, 7, 8. And then each time there's a new iteration, it goes and puts the 5 in the right spot, and it moves everything over. Then the next time, it's going to make the 3 and put it in the right spot. Okay? That is my high-level idea. Of course, the graphics are going to make a whole lot more sense. But it's going to go and put something in the right spot. It's going to move it down as long as it needs to be moved down. Okay? So that is the goal. So this is separate from selection sort, because if it's done up to index 3, then that means the first 3 original elements are in sorted order. It does not consider the other ones, which might be smaller still. Okay, so it's going to be n squared again. There are 2 loops, a for and a while this time, which is different, I guess. But here's what it looks like if I randomize the array. Let's do insertion sort now. So see how it's keeping the first elements sorted? Like, even though we have smaller ones way over here, we're only sorting the initial ones, those original elements. We're moving everybody else as long as we need to. And so if it's a very small element, it needs to be moved quite far down, you see. That is how insertion sort is working. And so this is the fastest n squared algorithm based on how it works, because it can stop early a whole lot of the time. If like it's got a big value, it can stay very close to where it started. So that's quite nice. And a very, very nice thing, if the array is already sorted or close to being sorted, insertion sort only takes linear time, because it's just got to go and make sure that everything's in the right spot. So if I run insertion sort again, it's just going to go through the array and be like, oh yeah, I don't have to ever move anything to the left. We're good. So that is fast, and it can stop early. That's a bit different from selection sort. It has to go and find the minimum still. See that? It doesn't know that it's done. So it's a very fun time talking about this stuff. You'll learn a whole lot more in CSCI 41. I just want to give you a taste of it now. Okay? Do read the book if you're interested in any of this, and I'm happy to talk about it too. So that's the 3 n squared sorting algorithms. Insertion sort is like the cream of the crop. Okay? Let's get into better ones though. Are you ready? So the next 2 algorithms are what are known as divide and conquer algorithms. And that unfortunately means that they're recursive. So if you hate recursion, I'm sorry. But it's a very, very efficient way to sort things, it turns out. So a divide and conquer algorithm, this is what it does on the array. Let's say it's 8, 6, 7, 5, 3. Is that an even number? Let's do O. What it does is it splits it in half, and then it recursively sorts each half. So it's going to turn it into 6, 7, 8, and it's going to work on each half. And 5, 3, 0, so 0, 3, 5. That is the idea for a divide and conquer algorithm. Okay, so it's recursive and it splits up the problems evenly and they don't overlap. So it sorts all these guys and it sorts all these guys, and then it worries about like bringing them back. One algorithm does it like this. Okay, then it sorts them all back. Okay, so you build up the solution using the results of the non-overlapping subproblems, if that makes sense. So this didn't overlap, this didn't overlap. We can build up the solution though by going through each of them, like going from left to right. Like, okay, which one's the smallest, 6 or 0? Let's take the 0. Okay, which one's smallest, 7 or 0? Sorry, not 7 or 0, 3 or 6. Oh, it was the 3. Okay, which one's bigger, 5 or 6? Oh, 5. And then we can take the rest of this because we're done with this one. 6, 7, 8. So that is divide and conquer in a large nutshell. That is the idea. Okay, and this algorithm that I just showed to you, in essence, is called merge sort. Okay, so what I just showed to you really was merge sort. Quicksort does it a bit differently. What merge sort does is it's divide and conquer. So it's going to split the array in half, and it's going to recursively sort this half, recursively sort this half into 6, 7, 8, and 0, 3, 5. That's the recursive part. And then it needs another helper function called merge that takes these sorted things, these sorted arrays, and brings them back together. Okay? 0, 3, 5, 6, 7, 8. That's the idea. Okay? So, unfortunately, this one actually needs some extra space. It needs a separate array to do the merging. And the reason why is, let me show you what would happen if you tried to merge these things in place. Let me show you that. So if we had 1, 5, and 2, 3, we tried to put those in the same spot. We're like, okay, what should we put here? Should we take 1 or 2 and put that in the first spot? Okay, we can keep the 1. Okay, should we put 5 or 2 in the second spot? Oh, okay, yeah, we can keep the 5. Or put the 2 here, make the 5 here. And then the issue is we think that we can take the rest of this, but we can't because the 5 is now out of order with the 3. We have lost the sortedness property. So that's not going to work, and we need separate arrays when we sort recursively. This is going to make a new array, 6, 7, 8, a new array, 0, 3, 5. And then we can merge them together into this bigger array. Okay? So, again, I don't want to spend too much time on this. It's just me hand-waving, and I'm sorry about that. But it's a very cool algorithm. I'd be happy to talk about it more. It's something that you will learn more about, though, in CSCI 41. And its complexity is n times log base 2 of n, which is a whole lot better than O of n squared. Log base 2 of n, we have learned, is quite a bit better than n, right? So let me show you merge sort and how it works. Let's randomize the array and do merge sort. And so here, you can see that it's recursing. It's sorted this left half. It's hard to see, and it's merging them. Now the entire left half of the array is sorted. It's working on the right half. Once it recursively gets that sorted, now it is, it'll merge the whole thing back. And it needed this extra space down here to do that. And it brought them back into the original array. Isn't that cool? And wasn't that fast? Okay, that was merge sort. And then the final one that I want to talk about, just to briefly go over, is called quicksort. Okay, again, in a nutshell, and I'm very sorry about that, but that is just all we have time for. So quicksort, what it does is it's based around this concept called partitioning. For reasons that I will talk about in a second, let me put, I don't know, let's put, I don't know, what should I put? 3 there, 6, 7, let's put 6 there and 8 here. That's my array. what quicksort does is it takes some element, usually it just picks like the first one, and it calls this its pivot. And what it does is it tries to swap the edge of the array with the pivot. So it tries to keep everything that is less than or equal to the pivot on one side of the array, and everything that's greater than the pivot on the other side of the array. So I guess it doesn't start there, it starts here. That one stays. And so it looks at these two, it's like, okay, which one belongs on the left side? So it's going to swap the 3 and the 8, and then it moves these arrows. Okay, 7, should I keep that? 5, which side should that be on? Okay, the 7 is bigger, it should be on the other side, and the 5 is smaller. So let's swap those, 5 and 7, and then it's figured out 2 halves of the array. One is bigger than the pivot, we got your 7, 8, and one is smaller than the pivot, you got your 3 and 5. And so now this half contains small elements, and this half contains big elements, and then it can recursively sort both halves. Recursively sort, recursively sort. Okay? And then no merging needs to happen for those, because these are already in the right spot. These are already on the right side. Okay? That is my very hand-wavy, again, high-level argument, but yeah, the idea is we know exactly where 6 should go after this. It needs to go right here. So the 5 can go there. We're going to swap it and put 6 there. And we know that 6 is in the correct spot now, because that was the pivot. And so we can recursively sort this half and this half up here. And that's the game. That's called quicksort. It is the fastest general purpose sorting algorithm. It's a bit better than merge sort, even though it's also n log n. Okay? So yeah, it partitions, and then it quicksorts those 2 smaller arrays that have values in similar ranges, but they're not yet sorted. Okay, so a lot depends, though, on the pivot, because if we picked like 3 as the pivot, we would have had a very small subarray on the left and then a very large subarray on the right to sort, and that wouldn't have been very good. So that sometimes we get O of n squared in very bad cases, but in most cases, in the average case, we say, usually when we run quicksort on an array, we get O of n log n time, we say. And that's quite fast. And usually, if we can get this good, and usually we can, it's faster than merge sort. There's a constant out in front usually, right? Remember, it was like 12 n log n or 18 n log n. The constant out in front of quicksort was the smaller one. Okay? So if I run this quicksort, here's its pivot. It shows this pivot and it's trying to put everything to the left side that's smaller than the pivot, and then it's recursively sorting this left side. And so now we have a sorted array over here. Let's pick a new pivot, sorting this array a little bit, that part's sorted. Now it's sorting the right half over here, and it is done in the blink of an eye. So it's all about those pivots. And I wonder if I can rerun it now. So it does sometimes take a while if you pick a bad pivot. Like, oh, okay, I need to put everything on the left side, or everything on the right side now, which is unfortunate. But quicksort works very, very well when the array is random, or you pick a random pivot. That's the idea. Okay, so see how it made a left half that was a bit bigger than the right half? It all averages out, though. And it's a very, very fast sorting algorithm. So I think that is all I have for you. Let's just watch this beautiful animation until it finishes. But yeah, that is quicksort in a nutshell. It finds an element to figure out where to put. And then it makes sure that the left half of the array has things smaller than that element, and the right half of the array has things bigger than that element. Okay, so that is everything. Again, I'm not going to test you too hard on this. I just want to give you a taste of all of this. If you would like extra things to do, let me give you some things. So, do you remember that brute force example with the horses, the pigs, and the chickens? That was very fun. Try and count how many basic operations that took, and try and figure out, using these rules for big O notation, like what it should have been. Big O of what? What should that be? Okay. Also, maybe take a previous lab and write a Makefile for it, because a lot of them used libraries, right? And so it would be nice to just say make instead of, okay, let's G++ this big thing. Yeah? It'll also save time. And then finally, try doing this. Try making a huge, large random vector using like rand and stuff, and then time the sorting algorithms on them to just prove to yourself that quicksort is the fastest, merge sort is the fastest. You can even do it with the searching algorithms too. Who is the winner on average? And that will help you learn a lot. And you can just use the ctime thing here for that. So that is essentially all I have for you. I will see you in your lab, but we've come far in this set of slides. So we've learned about searching through arrays, sorting arrays, and just trying to figure out how fast an algorithm is. All these searching algorithms, all these sorting algorithms, they have trade-offs. And we can use the language of complexity theory to figure out which one is better for a given task. So that is all I have for you, and I will see you in your lab.